Welcome to Topic 7. This is a relatively short topic with just 2 short videos, but there are quite a few experiments in this section, with 4 mandatory experiments that go through the various aspects of acid-base titrations. You will have heard of acids and bases before ever studying chemistry. We use them everywhere in everyday life. For example, fizzy drinks have a sharp taste because they are acidic. This is because they have carbon dioxide bubble through them, which forms carbonic acid in water. Alka-Seltzer contains a base, which we use to neutralize stomach acid when somebody has heartburn or an upset stomach. Toothpaste contains a base, which neutralizes the lactic acid produced by bacteria, which can cause tooth decay. Acids and bases are everywhere then, and contrary to popular belief, whilst they can be dangerous, they are mostly harmless and very useful substances. Some acids and bases can be dangerous, however. These tend to be the ones you see at either end of this scale, with very high or very low pH values. They would be described as corrosive, and they would always be accompanied by the appropriate hazard symbol. Having seen acids and bases at junior cert, you may remember that acids and bases are chemically different to each other. An acidic solution will turn blue litmus paper red, with no effect on red litmus paper. A neutral solution will not change the colour of either red or blue litmus paper, and a basic solution will turn red litmus paper blue, whilst having no effect on blue litmus paper. Before we go into more detail about what an acid is, however, we need to quickly talk about the element hydrogen. As you can see here, hydrogen has an atomic number of 1, and so it has 1 proton. A neutral hydrogen atom, therefore, will also have 1 electron. Hydrogen is unusual though, because to fill its outer shell, it would need to gain 1 electron to have the electronic configuration of helium. Hydrogen doesn't do this, however. It forms a more stable ion by actually losing its outer electron, to end up having no electrons at all. This means that a hydrogen atom consists of only the single proton in its nucleus. For this reason, we very often refer to a hydrogen ion as simply a proton, because that's what it is. As you can see, since hydrogen consists of only a proton, they are tiny particles with a very large charge for their size. For this reason, their behaviour is very unusual, and we have a whole branch of chemistry given to describing their behaviour. But why would a hydrogen ion form in the first place? Hydrogen behaves as a non-metal and mostly forms covalent bonds with other non-metal elements. Hydrogen, however, has a relatively low electronegativity value, so it sometimes finds itself bonded with more electronegative elements, which can pull the electron pair in the bond away from the hydrogen, so much so that the hydrogen is actually released without its electron in the form of a hydrogen ion or proton. What remains has a negative charge, since the atom that was bonded with the hydrogen has gained an entire electron. This process of releasing ions in solution is known as dissociation, and this brings us to our first definition of an acid. The first person to describe a theory of acids and bases was the Swedish chemist Svante Arrhenius. He proposed that an acid is a substance that dissociates in water to produce hydrogen ions. Let's consider the compound hydrogen chloride. It consists of 1 hydrogen atom covalently bonded to a chlorine atom as shown. The bond is a single covalent bond, as hydrogen and chlorine both have a valency of 1. The bond is polar covalent, however, and there is a significant difference in electronegativity of 0.9 between the chlorine and the hydrogen atom. When hydrogen chloride gas is bubbled through water, it is energetically favourable for the hydrogen chloride to dissociate into hydrogen ions and chloride ions. We call a solution of hydrogen chloride hydrochloric acid, because, as per our definition of acid, in water it dissociates to release hydrogen ions. We can represent this dissociation of the acid in the equation shown. On the left we have the undissociated acid, and on the right we have the liberated hydrogen ions, and what is left of the acid after the hydrogen ions have been removed, in this case a chloride ion. Here are some other examples of equations representing the dissociation of acids. Nitric acid, HNO3, dissociates to produce a hydrogen ion and a nitrate ion. Since in the case of hydrochloric acid and nitric acid, the dissociation of 1 mole of acid produces 1 mole of hydrogen ions, we refer to these acids as being monoprotic or monobasic acids. Since 1 mole of sulfuric acid dissociates to produce 2 moles of hydrogen ions and 1 mole of sulfate ions, we refer to it as a diprotic or a dibasic acid. Phosphoric acid dissociates to produce 3 moles of hydrogen ions and 1 mole of phosphate ions, and so we refer to this type of acid as triprotic or tribasic. The proticity of acids is important when we do calculations for reactions between acids and bases, as we shall see later. Because of the very small size of protons, they are too small to exist independently in solution. With their large charge and their tiny size, they are quickly pulled towards any negative charges that are nearby. The lone pair of electrons on the oxygen atom in a water molecule are an obvious and common target for dissociated hydrogen ions. A covalent bond forms between the oxygen and the hydrogen, forming what is called a hydronium ion, H3O+. This is the form that hydrogen ions actually exist as in solution. Indeed, all of the previous equations we looked at could be rewritten to include water in the equation. Chemists, however, for simplicity's sake, will still refer to hydrogen ions as protons, even though they know that they really exist as hydronium ions. For the exam, it is fine to write equations either way, but it is important that you know that a hydrogen ion does not exist independently in water, but rather becomes incorporated into water molecules to form hydronium ions. We can write a general equation for the dissociation of an acid, where the acid is composed of a hydrogen atom and the rest of the molecule is represented as A. A, as you can see, will always have a negative charge after the proton is lost. Arrhenius also defined a base in a similar way to acids, but rather than hydrogen ions, he defined a base as a substance that dissociates to produce hydroxide ions. What is a hydroxide ion then? A hydroxide ion is a polyatomic ion made up of one oxygen atom and one hydrogen atom, with an overall charge of 1-. You will have seen many hydroxides by now, and will have noticed that they are usually bonded with a metal ion. You will certainly have come upon sodium hydroxide, NaOH. Metal hydroxides are ionic compounds, and so they will exist in the form of ionic lattices. If we dissolve sodium hydroxide in water then, it will dissociate to give 1 mole of sodium ions and 1 mole of hydroxide ions. We therefore would refer to sodium hydroxide as being a monoacidic base. Other examples of hydroxide bases include magnesium hydroxide, MgOH2. Magnesium hydroxide dissociates to release 2 moles of hydroxide ions for every mole of magnesium hydroxide, and so we would refer to it as being diacidic. Lastly, a substance like aluminium hydroxide, which dissociates to give 3 moles of hydroxide ions, is referred to as being a triacidic base. Again, we will see how the acidity of a base, how many moles of acid they react with, and the basicity of acids, how many moles of base they react with, are important when it comes to the stoichiometry of neutralization reactions. We can again represent the dissociation of bases into metal ions and hydroxide ions with the general equation shown, where M represents a metal element, which forms a positive metal ion in solution, M+, after dissociation. With time, it became clear, however, that Arrhenius' definition of acids and bases was limited, largely because it limited acid-base reactions to happening only in water. And of course, there are many acid-base reactions that don't require water. Johannes Bronsted and Thomas Lowry independently proposed a new definition of acids and bases, which had a more general application than the Arrhenius definition. They proposed that in chemical reactions, an acid acts as a proton donor, whilst a base acts as a proton acceptor, and in this way they react with each other because they cannot react without the other. If an acid is to lose a proton, there must be a base to accept the proton, and if a base is to accept a proton, well then there must be an acid present to donate it. Let's take a look at some examples to see what this definition means in more detail. If we revisit the reaction between HCl and H2O, we can now look at the same reaction in a different way. Here we can see that when HCl comes in contact with water, that it loses or donates its hydrogen atom, or in Bronsted-Lowry terms, a proton. This proton is accepted by the water molecule to form H3O+. In other words, the HCl has donated a proton and is a Bronsted-Lowry acid, and the water has accepted a proton and is a Bronsted-Lowry base. What about the reaction between ammonia and water? Here you can see that water donates a proton to form a hydroxide ion, and this proton is accepted by ammonia to form NH4+, the ammonium ion. Therefore, water acts as an acid, since it donates a proton, and ammonia acts as a base, since it accepts a proton. You will notice that in the previous reaction, water was a base, and in this reaction it is acting as an acid. There are many substances that can act as an acid or a base, depending on what it is reacting with. These substances are described as being amphoteric. If we now react the acid from the first reaction, HCl, with the base from the second reaction, NH3, we can see how Bronsted-Lowry acid-base definitions do not require water, and so are an improvement on the Arrhenius definition of acids and bases. Here you can see that HCl donates a proton and is a Bronsted-Lowry acid, and this proton is accepted by the ammonia to form an ammonium ion, NH4+, and so ammonia is a Bronsted-Lowry base. We can represent Bronsted-Lowry acid-base reactions with general equations also. An acid is represented by HA, where again the hydrogen is the proton that will be donated, and the A is the rest of the molecule. When the proton is donated, the remaining part of the molecule will have a negative charge since it has lost the proton. A base can be represented by B, and it will accept the proton to form BH+. Note that the charge of the base after accepting the proton will be positive since it has gained the proton. We can combine both these equations into one to show a full Bronsted-Lowry acid-base reaction. Let's now examine this general equation in a little more detail. You can see clearly that the proton in red is transferred from the acid, the proton donor, to the base, the proton acceptor. Again, remember that you can tell from the change in charge what has lost a proton and what has gained a proton. Here you can see that the acid has lost a charge of +1, going from a neutral charge on the left to a negative charge on the right. We would know from this also that it is the acid, though it is probably easier to spot that it has simply lost a hydrogen atom. Conversely, for the base, it has gained a charge of +1, going from neutral on the left to a charge of +1 on the right. We would know from this increase in charge that it is a base, though again it's probably easier to see that it has gained a hydrogen atom. But what if this reaction could run in the opposite direction, such that the reactants on the right could react to form the products on the left? Many reactions in chemistry can in fact run in both directions like this. If we consider this, we now see something interesting. The BH+ will be the acid if the reaction runs from right to left, as it is the only species that is in a position to donate a proton. Similarly, A- will now be a base because it is in a position to gain a proton. So A-, which is what is left of the acid HA after donating a proton, is now a base. And BH+, which is what the base becomes after gaining a proton, is now an acid. If we now go back to the previous direction of the reaction by reversing the arrow, we see that on the left side of the equation we have an acid that produces a base on the right side of the equation, and we have a base on the left side of the equation that produces an acid on the right side of the equation. In other words, an acid turns into a base when it donates a proton, and a base turns into an acid when it accepts a proton. These pairs of acids and bases have a special relationship with each other, such that we have specific names for the acid and base on the right side. They are called conjugate acids and bases. An acid produces a conjugate base, and a base produces a conjugate acid. Together they are known as conjugate acid-base pairs, and every acid-base reaction has two conjugate acid-base pairs, as you can see here. It should be clear from here that a conjugate acid-base pair is an acid and base that differ by only one proton, and this is the rule to remember when answering questions in the exam. Questions tend to ask you to identify the conjugate acid or base of a given substance, or identify a conjugate acid-base pair from a chemical equation, as we've seen. Let's have a look at some examples. A table is the best way to work with conjugate pairs. Here you can see in the central column that we will have a given substance. Whether it behaves as an acid or a base, or both, will be indicated by its colour. In the left column, we have a base formed from an acid by the loss of a proton. In the right column, we have an acid formed from a base by accepting a proton. We'll start with some acids. All of the substances you see here can only behave as acids, as they are only in a position to donate hydrogen atoms. They cannot accept protons as their structures do not allow it, and so they cannot behave as bases. Hydrochloric acid will lose its only hydrogen atom to form the conjugate base Cl-. HNO3, nitric acid, will lose its only hydrogen atom to form its conjugate base, the nitrate ion, NO3-. Ethanoic acid will lose its hydrogen atom bonded to the very electronegative oxygen to form the ethanoate ions, CH3COO-. Sulfuric acid will donate a proton to form HSO4-, and H3PO4, phosphoric acid, will donate a proton to form H2PO4-. Note that in all these examples, the acid and its conjugate base differ by only one hydrogen atom. So if you are asked to write the conjugate base of an acid, all you must do is remove a hydrogen atom and add a charge of 1- to whatever charge is already there. If it is neutral, it will have a charge of 1-, but if it is already charged, then you will add a charge of 1- to the existing charge. Let's look a bit more closely at the last two examples with sulfuric acid and phosphoric acid. We saw already that sulfuric acid is diprotic, in that it can actually donate 2 hydrogen ions, and phosphoric acid is triprotic, so that it can actually donate 3 hydrogen ions. When we are finding the conjugate bases, however, we only remove 1 hydrogen atom from whatever acid we are looking at, because a conjugate pair differs only by 1 hydrogen atom. The bases we see here are only in a position to accept protons, and so cannot behave as acids. Ammonia, NH3, accepts a proton to form the ammonium ion NH4+. The hydroxide ion accepts a proton to form water. Note in this example that there is already a charge of -1 on the ion, so accepting a proton will mean that the final charge is now neutral. The next compound, ethylamine, is not a compound that you will see on this course, but it is nonetheless easy to find its conjugate acid. All we must do is add a hydrogen atom and a charge of +1 to form C2H5NH3+. Sulfate ions behave as bases in accepting a hydrogen ion to form HSO4-, and phosphate ions act as a base in accepting protons to form HPO4-2-. Notice before that while sulfate and phosphate ions can and do accept multiple protons, their conjugate acids are formed when they accept only 1 proton. So in all these examples, the base and its conjugate acid differ by only 1 hydrogen atom. So if you are asked to write the conjugate acid of a base, all you must do is add a hydrogen atom and add a charge of +1 to whatever charge is already there. If it's neutral, it will have a charge of +1, but if it already has a charge, then you will add +1 to the existing charge. Lastly, we will see some examples of amphoteric substances, substances that can behave as both acids and bases, depending on what they are reacting with. Water is probably the most famous example of an amphoteric substance. You can see that it can act as an acid, donating a proton to form its conjugate base OH-, or it can act as a base, accepting a proton, to form its conjugate acid, the hydronium ion, H3O+. Note that there are 2 conjugate acid-base pairs shown here. One pair is the hydroxide ion and water, and the second pair is water and the hydronium ion. Both these pairs differ only by 1 proton. Hydroxide and the hydronium ion are obviously not a conjugate acid-base pair, as they differ by more than 1 proton. They differ by 2. Ammonia too can behave as an acid or base. It can accept the proton as a base to form its conjugate acid, the ammonium ion, NH4+, or it can act as an acid, donating a proton to form NH2-. H2PO4- can accept the proton as a base to reform phosphoric acid, or it can donate a proton as an acid to form HPO4-2-. Note in the next line, if we now take this HPO4-, it can act as a base to reform the acid from the previous example, H2PO4-, or it can further dissociate as an acid, donating a further proton to form the phosphate ion, PO4-3-. Similarly, HSO4- formed during the dissociation of sulfuric acid can act as a base to reform sulfuric acid, or it can further dissociate as an acid, donating another proton to form the sulfate ion, SO4-2-. In all these examples, the center and left column represent conjugate pairs, and the center and right column represent conjugate pairs, as they differ by only 1 hydrogen atom, or we would say 1 proton. That's it for section 7.1. Have a go with the questions.